welcome back. Today we're going to take a look at how to do some quantitative distribution testing in the R programming language. In particular, we're going to be taking a look at how to conduct a Kolmogorov-Smirnov Lilliefors test and a couple other tests that are closely related to these two tests as well. So what I've gone ahead and done is I've created a data set just for us to work with. You can either work with one of your own data sets or randomly generate one, preferably from a uniformly distributed data set or possibly even a normal distributed data set. It really just sort of depends what you want to observe in this demonstration. So what I have here in this data set is a bunch of different vitamin profiles for 60 individuals, and what I want to do is extract one of these variables to test whether it comes from potentially a normal distribution or not. So in particular, the vector that I'm going to be looking at is the thiamine levels for this set of 60 individuals, and our values are ranging anywhere from say 9 up to 13 or something like that. So one of the questions that you could claim or moreover a null hypothesis that you could specify is that X comes from a normal distribution with a mean of 10.5 and a standard deviation of 1.2, with the alternative hypothesis that it doesn't come from this particular distribution. So the test, at least the first test that a lot of people do, is usually referred to as a Kolmogorov-Smirnov test. And in order to conduct a Kolmogorov-Smirnov test, we need to construct the empirical quantiles, the theoretical quantiles, construct the cumulative density functions for those two sets of quantiles, and compare those CDFs to one another and see if they match up closely or not. And I'll show you how to generate a graphical representation of these test statistics as well, so you can sort of get both a numerical and a graphical interpretation of what's really going on here. So the first thing that you definitely want to do is to sort this data set from least to greatest. As you can see, we have 12, 9, 12, 12, 11, 9, which is definitely not from least to greatest. So I'm going to be creating a set called XS, which is going to be the sorted vector X, and we can easily do that in R by doing sort of X. So that's going to sort that data set from least to greatest, so 9.82 is the minimum, 12.99 is the maximum in milligrams for our thiamine levels. And what we need to do probably is also count how many values are in this vector. I know that there's 60 values in this vector, but sometimes it's just safer to code this just in case you want to just throw in another vector into this blindly without having to analyze anything in particular. So in this particular data set, we have 60 values, which is obvious from the environment window in R. But now what we want to do is we want to construct an artificial normal distribution data set that has this particular mean and this particular standard deviation. All right. So what I want to do is construct my empirical cumulative density function, or CDF for short, and I'm going to calculate this as f of x. So f of x is going to represent my empirical distribution, and fx is going to be based on a particular domain that is normally distributed. So I can easily construct a normally distributed data set using the qnorm function, just like we did with normal quantile plots. So I'm going to do qnorm, and then I'm going to generate a sequence from 1 to n, all divided by n plus 1, because if we have n points, that should partition our normal distribution into m plus 1 regions, such that the area between any adjacent normally distributed points is equal to the same exact value. So what I want to do is just do a sequence from 1 to n, and I want to increment that by 1, and I want to divide that by m plus 1 for each of those data points. And I want to generate these normally distributed data points with respect to a mean of 10.5 and a standard deviation of 1.2. And that's going to give me my normally distributed data set. And what I want to do is I want to calculate the probabilities to the left of those values. And you probably should know what these probabilities are, but I'm just going to do it just in case you aren't exactly aware of what those numbers are. But that would be p norm of those normally distributed values, again associated to a mean of 10.5 and a standard deviation of 1.2. All right, so that is going to give me my empirical quantile for a data set of size n that is associated to this particular distribution. Now, what we want to do is we want to calculate the probabilities associated to our sample values with respect to this mean, standard deviation, and distribution, and see if these CDFs match up with one another. So the next thing I want to build is my theoretical CDF. And this is going to be equal to, I'm going to call it psi x. So psi x is going to be compared to fx. And this is going to be equal to p norm of my sample values sorted from least to greatest with respect to a mean of 10.5, a standard deviation of 1.2. And let's just make sure that it's doing these probabilities with respect to the left tail. Lower tail is equal to true just to be safe. And you could have done it up here on line 17 also, just in case you want to be a little bit careful, because sometimes R may default it to the right tail, left tail, or it might do something very strange sometimes. So what we have here is our empirical quantiles stored in f of x, our theoretical quantiles, or cumulative density functions, which is stored in psi x, and all of these values should be between 0 and 1 in a monotonic increasing pattern, because as you move from left to right, you start off with 0% of the data and work all the way up to 100% of the data in the maximum spectrum of that distribution. So we have fx and psi x. fx, what we want, psi x, what we have. Is there a significant difference between these CDFs? That's the question that the Kolmogorov-Smirnov test statistic is going to try to answer. So what I want to go ahead and do now is generate a graphical display of actually what we're looking at here. So what I'm going to do is I'm going to plot our normal distributed data set, NX, and their associated CDF values. And let's give this a nice title. So this is going to be our empirical and our theoretical CDFs for our data sets. And PCH is equal to 1 is just going to be that open circle. CX is equal to 0.8 is just going to be that size. And that's going to give us our empirical distribution. So this is the distribution that we would like our data set to follow if it was truly normally distributed with that particular sample size. Since there is a little gap between these points, I want to sort of simulate what the continuous version of that would look like. So what I'm just going to do is I'm going to connect each of those points with lines, and I can easily do that by just calling the lines command. And let's actually color those lines. Let's say steel blue, and let's make those lines a little bit more thicker than our point. So that's the LWD is equal to 2. So that gives us our empirical distribution. Now what I want to do is I want to plot the points of our theoretical values, which is going to be nx, the same exact domain, and psi x, the probabilities that we actually have for our data points. And we're just going to plot that right on top of the data. That's why I'm using points instead of plot. Let's do a PCH of 1 and a CX of 0.8, same exact style as the other point. So those are those points that are sort of scattered above. And also let's connect those points, so NX and psi x, with a different color. Let's choose, say, violet red. All right, let's do the same width of 2. So that is going to be our theoretical distribution. Obviously, we can see that these two distributions are not equal to each other, but what these distribution tests are going to be helping us to answer is, are they significantly different from each other? So what we do is we look at the vertical distances between the theoretical and empirical CDFs. So in order to calculate each of those distances, since our psi x and our fx are already stored as vectors, we can create a vector of distances, which I'm going to be storing in D, as the absolute value of our theoretical distribution minus our empirical distribution, and that's going to give us our distances. Keep in mind CDFs are bounded below by 0 and bounded above by 1, therefore each of these distances should also be between 0 and 1. If these two distributions are always equal to each other, all these differences should be equal to 0, which is what we want. So what we're going to be looking at in this set of distances is to see if we have any substantially large distances, because that's definitely going to be a flag to indicate that these distributions are not equal. So what I want to do is calculate the Kolmogorov-Smirnov test statistic KS stat, which is just going to be equal to the maximum of these absolute distances. In this case, that's going to be equal to 0.23. Since it's bounded above by 1 and we want these to be close, we typically do not want our Kolmogorov-Smirnov test statistic to be substantially large. Usually comparing to 0.1 is pretty good, but if you don't know the distribution of a Kolmogorov-Smirnov distribution, you can always run a Monte Carlo simulation on this particular type of distribution to get your, say, empirical critical values in order to compare your test statistic to, in order to reject or fail to reject that null hypothesis that the sample does come from this this particular normal distribution, right? But obviously we have 0.23, and that's significantly greater than 0.1 when we say. So if we choose 0.1 to be our critical value, then we will reject the null hypothesis that our sample does come from this particular normal distribution. Now, it's very important to take note that the Kolmogorov-Smirnov is associated to the maximum distance between these two distributions, and that maximal distance could be associated to an outlier of our sample distribution. Therefore, it's very sensitive to outliers. So instead of comparing or looking at the maximal distance between the empirical and theoretical CDFs, what we can do is look at the cumulative distance between these two distributions across all points on our domain. So one test statistic that takes that into consideration is referred to as the Cramer-von-Mises distribution or test statistic. So what the Cramer-von-Mises test statistic is it looks at each of the distances, it squares them, and sums up all of those squared distances. We can easily do that in R by doing just sum of d squared. So in this particular case, we have a Cramer-von-Mises test statistic. I guess I should be calling it CVM stat. And we have a CVM stat of 1.1. And you can ask, well, is that large or is that small? So since each of the distances is bounded below by 0 and bounded above by 1, when you square that, that's still bounded below by 0 and bounded above by 1. And when you add up n of those points, the upper bound would be n, the sample size, and bounded below by 0, right? That means they match exactly, and if it's equal to n, that means they're always n apart, which is very unlikely, but in some sense possible, right? So generally speaking, if you have a 1.1 cumulative distance, that means across all of your points, these curves are practically maximally apart at only one point and matches exactly at all other points, which could be viewed as substantially large, right? So what you can do is say, consider, 1% of your sample size is sometimes a good starting point, and that's zero point 0.6. So if you have a cumulative CVM test statistic bigger than this, maybe it's too big. But again, as usual, if you don't know the distribution of your Cramer-von-Mises distribution, you could always run a Monte Carlo simulation to sort of get an idea of what that looks like. Or you could just choose your own critical value by looking at your distribution, say 0.6, and then reject or fail to reject based upon that claim. But the null hypothesis for Cramer-von-Mises is still the same. Now, most of the time, if they are associated to a similar shape, these tails are always going to match. Look at my right tail, it matches almost perfectly, but my left tail has a really big gap, and that's usually a really, really big flag when it comes to equality of distributions. So what we can do is penalize those distances on the left or right tail, if it happens to be present, a little bit more heavily. That is, multiplied by a really, really big number. So to keep in mind, the cumulative density value on the left tail is equal to 0, and the cumulative density value on the right tail is equal to 1. So if we divide by 0, that's going to make our number arbitrarily large. And keep in mind, we're not dividing exactly by 0, but something really, really close to it. So something really, really close to 0, and something really, really close to 1 minus something really, really close to 1 from the left-hand side. So a test statistic that sort of takes this into consideration is what is referred to as the Anderson-Darling test statistic, which I'll just abbreviate by 80-stat. So 80-stat is going to be equal to the sample size n times the sum of our squared distances. So it sort of starts off with a CVM approach, but now we're going to be dividing by our empirical distribution, which is going to be our let's call it fx. And then we're going to be multiplying that by 1 minus fx. And if our fx value is really close to 0 or 1, then either one of these is going to be close to 0, and that's going to weigh that distance, if it is non-zero, a lot more heavily. So in this particular case, we have an 80 test statistic of 379.8, which is typically normal because the Anderson-Darling test statistic is bounded below by 0, but not bounded above, so it could go up to infinity or some quasi-infinite amount. Great. So this you definitely probably would have to do a Monte Carlo simulation to get a sense of how large is large. But nonetheless, we want that number to be as small as possible in order to have evidence that this sample does come from this particular distribution of interest. Now, one thing that really clusters these three methods together, the Kolmogorov-Smirnov, the Cramer-von-Mises, and the Anderson-Darling test statistic, is that they're all testing the claim that our sample comes from a particular distribution. In this particular example, we're doing a particular normal distribution. Now, if you're interested in the claim that our sample comes from any normal distribution, so emphasis on the word any normal distribution, regardless of the mean, regardless of the standard deviation, then we're going to be using what is referred to as a Lilliefors test. Right, so the Lilliefors test is a little bit more easier to pass because regardless of the distribution, as long as it's normal, it could be any mean, any standard deviation, it will pass the Lilliefors test. Right, right. Whereas the Kolmogorov-Smirnov, it has to satisfy a particular mean, a particular standard deviation, a particular shape. Here, it's any normal will work. So what we want to do, instead of comparing our sample to every single possible normal, which is practically not possible, what we need to do is first standardize all of those things into the standard normal world and compare our standardized sample to all of them at once in the standard world. So the thing I need to calculate would be the z-score of my sample, which would be our sorted sample minus the mean of our sorted sample, all divided by the standard deviation of our sorted sample. That's going to give us a data set whose mean is equal to 0 and standard deviation is equal to 1, as expected. And then we need to calculate the empirical distribution that a data set of this size should follow if it were to follow a standard normal distribution, sort of like we did before. So I'm going to call this set NZ for the domain values, which is going to be Q norm, and then we're going to do a sequence from 1 to n by 1, all divided by m plus 1, so it has the same exact structure, but now we're going to be comparing this for a standard normal distribution, which defaults to 0, standard deviation of 1. So that's our NZ. Then what I want to do is calculate the probabilities associated with each of those values. So that's going to be our FZ. And I'm just going to do a P norm of NZ with a mean of 0, a standard deviation of 1, and let's just make sure our lower tail is calculating from the left-hand side. Sorry, and that's going to give us our empirical probabilities. And then let's calculate our theoretical probabilities of what they actually are for our sample. So we're just going to do P norm for our z-scores generated from a mean of 0, a standard deviation of 1, and let's just make sure that that again is a lower tail is equal to true calculation. So let's take a look at what the CDF plots for our standard normal world looks like. Notice that for our original Kolmogorov-Smirnov test statistic that the mean or the median for the red doesn't exactly line up for the blue. Right? So if the means aren't equal, then the distributions likely aren't going to be equal either. So this is usually going to centralize our magenta curve around our blue curve most of the time if it happens to be normal. So what we're going to do is we're going to plot NZ, FZ, and then we're going to title it, say, main is equal to our empirical and theoretical standard normal CDFs for our data sets. And then we're going to set a PCH of 1 and a dot size of, say, 0.8. Right, so it's going to have the same exact shape just as before. The only difference is the domain is different, but the cumulative values are going to be the same because of the same exact sample size. So then we're going to connect those points with lines. So NZ, FZ, color equals blue. and then LWD is equal to 2 for that line width. So that's our empirical CDF. And then we're going to plot our points for our actual sample, which is going to be NZ psi Z PCH is equal to 1, and then a dot size of, let's say, 0.8. So that gives us those points. Know that it's sort of centered around the same exact point, a little bit closer to 0 than it was before. It's going to match a little bit better, because as long as it's from a normal, doesn't matter which, then it will pass the Lilliefors test. So let's just connect those black points with lines. So let's do NZ psi Z, and then let's color those lines, say, violet red, just like before, so that at least our pictures are comparable. So we get that particular theoretical CDF. So let's calculate our distances. Notice that our distances are quite different. We have a lot more discrepancy between these cumulative density functions, but these CDFs are a little bit more closer to each other, because Lilliefors, again, is a little bit more easier to pass, because we're comparing to infinitely many distributions, not just one. So our standardized distances, let's call that dz, is going to be the absolute value of psi z minus fz, and our Lilliefors test statistic is the same exact thing as the Kolmogorov test statistic, so it's going to be the maximum value of dz. So our Lilliefors test statistic is going to be equal to 0.12. And if you remember our Kolmogorov test statistic before, it was 0.23, which was usually agreeable to be substantially large, and our Lilliefors test statistic is a little bit more smaller, almost half of what it used to be. Right? Now, is that still bigger than 0.1? Yes, but if you had a cutoff value of, say, 0.15, then you would have evidence to believe that it comes from a normal, but it doesn't come from that particular normal that we specified before. And of course, you could consider, say, a Cramer-von-Mises or an Anderson-Darling approach for this particular calculation, because we could sum up the squared distance scores and then weight these tails a little bit more heavily. But keep in mind, it's already a lot more easier to pass the Lilliefors test, so you don't want to make it too easy to pass, else you're practically going to be always accepting the fact that your sample is coming from a normal distribution when it likely is not coming from one. So that's how you would do some quantitative distribution testing in the R programming language. Hope you enjoyed this video, and I'll see you in the next one. Take care.